Okay, now it should work. Good. All right. So the three things we need to have to say we have a causal relationship of some sort. And that's what we're after, isn't it? We're after this is different from this. This causes this. We're not after let's describe something. That's not what we do. We're doing science. So we're trying to say this causes this. We're trying to make causal statements. Okay? Unlike other disciplines, don't do that, that's fine. That's what they do. But in ours, we're trying to make causal statements. Temporal precedence. In other words, the cause must come before the effect. We have to eliminate alternative explanations. And of course, that is something that's important. That's important. Both of these are important in experimental design. And we have to have covariation. We have to say that as one changes, as the cause changes, the effect changes. We need these three things. This is probably stuff you learned about in 2127. So you need temporal precedence, elimination of alternative explanations, and covariation. Questions so far? You've heard this before. I think you probably heard this story before. Okay. The first two can easily be dealt with through design. Especially if you're doing an experiment, obviously you put people into groups first, then you measure them. There you go, temporal precedence. Eliminating alternative explanations, that's just clever experimental design. That's how do we usually do that? We control everything and vary one variable, and we randomly assign people to groups. I have now just in 45 seconds taught you 2127. How anyone does poorly in that class is so far beyond me. That said, people do, and it happens, and I guess it's a thing, but it's the same thing over and over again. Randomly assign people to groups, control stuff. Next class, randomly assign stuff to groups. Control things, move on. I know that doesn't sound like Cheryl at all. I taught that course last time I taught it was 1997. It's been a while. But I wasn't really doing a Cheryl. I'd have to do it much shorter. No, we all make fun of each other. Don't tell Cheryl I said I'm very frightened of her. So let's make up some data. I don't know what these are. I don't care what they are. Let's say they're scores on a thing. I don't know what they are. I don't care. It doesn't matter. But we got a mean of 66.2 and 71.6. Standard deviation of 7.85 and 8.56. Okay, that's great. Whatever. Again, it really, really doesn't matter. If this is something that, they're tests, okay? And one group was taught one way, one group was taught a different way. If that makes you happy, if you have to visualize people being put into groups, it's that. They're just numbers, guys. You know. If I don't say that, though, eventually someone goes, well, what do those numbers represent? I don't know. They're just numbers I typed. They're numbers. They represent my typing. When I made these slides up like 4 years ago. This was the last course that I switched over to using slides. Before that, overheads. Awful. More than 4 years ago. 2007. 8 years ago. Holy shit. No, it's amazing how long I've been doing what I do for a living, that's all. That was like 29. Holy crap, that's 20 years. Okay. So here's a question for you. Here's a distribution with a mean of 72. And a standard deviation of, I think, 6. Is that 6 or is it 8? Could these two sets of scores, one with a mean of 72 and one with a mean of 71.5, whatever it was the other mean 68 point something? Who gives a crap? They're two pretty close numbers. Could they both have come from this distribution, those two sets of scores? Well, look. Look where the big meaty part of the curve is. It's right here. They both come from that big meaty part of the curve where most of us live. Right? They don't come from the tails. They don't come from way over here. One group didn't have an average of 40-something. One group didn't have an average of 104. Well, that's obviously not a test. Can't get 104 on the test. Sure you can. It's at 105. A friend of mine, I think I told some of you guys this, used to teach math. And I was a school principal, but he used to teach math. And students would always ask the same question. Test coming up, and they'll say, "What's it out of?" Like that matters. And he used to make tests out of like 107,000. And they go, "Oh, yeah, the first question's worth 34,000 points." Just to, and he said, eventually someone would go, "Ah, I see what you're doing." But like people would freak out for a while. So, do we have, no, any of those means, they were what, 68 point something, 72 point something? They're both right over here. It seems pretty likely that those two means came from this parent population distribution, as we would say. Do you see the logic that I'm using here? Does that make sense? Okay. We just made a decision. There's a relatively small, usually less than 5% chance that two sets of scores come from the same distribution. We usually say it's unlikely to have happened by random chance alone, and therefore we have what we call a statistically significant effect. Without significance, we do not have covariation of x and y. Or we do not have enough evidence to say we have covariation of x and y. Okay? Without that, without statistical significance, we cannot have the confidence to say that we have covariation of x and y. Now, one can make a case here. And as I said here, usually it's less than a 5% chance, that that's ridiculous. In fact, I think one can make a very strong case for saying it's ridiculous. Why should we care only about a chance of 5%? Is 5.5% not good enough? Right. Why is 0.04999999 better than 0.05000001? It ain't different by much. Or for that matter, why is 0.04 better than 0.06? It's not much. So it's a question, and that's a discussion we can have. But I'm saying that typically what we do is we care about 0.05. We care about a 5% chance that two things do not come from the same distribution. Why do we have this variation in the first place? Well, because, and it's not just, people always say it's measurement error, psychology isn't precise. That's bullshit. It's not that. It's partly that. That's something to be said for it. But mostly it's because people are different. Animals are different. Light bulbs are different. Things are different. Okay? So if we had, let's pick what's a variable that seems like there wouldn't be any difference between a group of this in this class and a group of a similar sized class in history. I don't know. Do they have let's say I don't know. It's unlikely that height would be different, isn't it? It's pretty unlikely. Even better. Let's use the left half of the room and the right half of the room. Even better. It is certainly possible that there is a difference here, that one half of the room is taller than the other half of the room. Possible. If I choose 3 people to represent this side of the room, and 3 people to represent this side of the room, I'm not doing enough to come up here. I'm not measuring anybody. That would just get weird and kind of sexual harassing if I start measuring people, so I'm not doing that. Men or women, I'm not doing that. I'm not, there's none of that. That's not, I shouldn't have even said it. There's going to be protests. An indignation committee will be formed. But if I randomly pick, and let's just say it is random, but randomly I end up getting, let's see. I get Lucas. Yeah, so he's a pretty tall guy. And let's see, it was too tall. You look pretty tall and pretty tall. So you 3 guys, and that's your group. And then over here, I pick Let's see, Jade, because she's not very tall. Who else am I going to pick? And we're pretending this has been done randomly. And Romy he's not very tall. And let's see, anybody else? No, Spencer's not tall. Lead on gender specifically. Well, we're not going to only pick women for men being all nice and good. And then we say, look, guys are taller on this side, the guys are taller on this side. And you say, that's bullshit. Just because randomly it turned out that you got these guys. And you got these guys. That's just random chance. Because next time, when do we get Tom? Tom's taller than anybody in the room. Right? Tom's pretty tall. So we pick random people. This time we get Tom. Then we get other taller people. And this time we get the short people. Here, Cassidy shows up. So then we get shorter people. The center is tall. But really, you probably come from the same parent population distribution of third-year psychology students. Right?
I think it sounds like boring.
Yeah, well, yeah, and most of you weren't quite boring. But still, but the point is, we're picking, if we're doing it, again, pretending that was random, and it wasn't. But I'm saying that could happen. That could happen. But that's simply because of variation in that's just called sampling error. And when you call it error, it makes it sound like it's a mistake. It's not a mistake. Okay? It's just because of random sampling. So it can happen that we get what looks like a difference, but really it isn't a difference. And that those differences that I found, we get 9 people here. That'd be pretty rare that could happen, that I could get those exact 3 sets of people on both sides. Some quick math in my head, it's exceedingly unlikely, but it's possible. It could happen. Well, it's 9 factorial divided by 3 factorial times 13 factorial divided by 3 factorial. It's exceedingly unlikely, 1 over that. That's an exceedingly unlikely number, but it could happen. It could happen. I mean, for those exact 3 people on each side. Picked in that exact order I did it, I should have been multiplying each times 9. Anyway, it doesn't matter. I learned in grade 13 algebra. But it could happen, right? So, on the other hand, does anybody know what the major is of most basketball players? I don't know. I haven't looked. The last couple of years it was sociology. Is it still, I think? Because I know one of the sociology profs actually sort of acts as their kind of tutor. So I think a lot of it's that. I don't know. I'm just guessing. Maybe like sociology. Let's pretend 9 of the 12 guys in the basketball team are sociology majors. Let's just pretend that. Now we could probably say, if we randomly picked, say, sociology students are taller than anybody else on campus. It's probably actually true. Because their parent distribution has a bunch of basketball players in it.
And then we have Jamal.
Right? And we have Jamal, who's a basketball player, and he's not as tall as I am. So, got a good head for the game. So it's interesting. This is the kind of decision we make, except we do it using math rather than using, and pretty simple math, rather than just using, those look like they could come from the same place. Right? So does that make sense? So that's sort of the logic of hypothesis testing, right? So what we do is we set up 2 mutually exclusive hypotheses. Mutually exclusive meaning it can be one, but not the other. You can't be both. We set up HO, or H sub O, you'll hear people say sometimes. That's the null hypothesis. And up until a few years ago, up until about 15 years ago, when this word took on another meaning, people call it HO. But they don't say that anymore because it's got connotations. People don't like it. But seriously, people used to say HO. Because they say ho and ha. But no one says that anymore. Because, it's not nice. It's not nice to call an hypothesis a ho. You're probably oppressing it. The alternative hypothesis, each sub 1 sometimes too, 0 to 1. Ho ha. Ho ha ha. It's the hypothesis song. Ho ha ha ho. I have to keep myself entertained. I have to stand here and talk for 4.5 hours today. So I have to do something to keep myself somewhat entertained. It's going to be so nice on days when you guys have quizzes and tests. I know you guys don't think so, but I do. And frankly, I don't care about you people. It's a joke. I care about 3 or 4 of you guys. So, the null hypothesis is that nothing happened. There is no difference. The 2 groups come from the same parent population distribution. By the way, those 3 things all mean exactly the same thing. You're saying I'm redundant? I repeat myself? I say things over and over again? Yes. The alternative hypothesis. The groups are different. They come from different parent population distributions. Again, those 2 things mean the same thing. Because the groups are samples of the population. And see, this is why we use, going back to what I was talking before with the height example, this is why we use random sampling. Because using random sampling, it's exceedingly unlikely to get Craig and to get Lucas at the same time. It's not going to happen. It could happen, but it's unlikely. Even out of 9 people, picking 3 people, it's unlikely to get those 2 guys together. Now, the thing is, there is a reality that 2 groups are different or 2 groups are the same. In other words, HO is true or HA is true. That's just the way the world, it's a thing. Don't go on with there is no reality. Everything's subjective, man. Get out of here. You shouldn't even be in the sciences if you're thinking that. You should go, I don't know, go write poems. That's great. It's perfectly useful. We need poets in the world. That's great. But you shouldn't be sitting there. There really is no reality. Oh, shut up. Now, our perceptual world is certainly created by our nervous system. I understand that. Sure. How do you know the red that you see is the same as the red that I see? What are you, high? Yes. You haven't, see, you may think that you thought of that the first time you got high. No, people have been saying that ever since people have been getting high. So, HO can be true, HA can be true. Then you make it, that's reality. We don't ever really know it. How often are we ever actually able to look at a whole population? In our theoretical example here, the right half room, the left half room, we can, because we can actually look at everybody. We wouldn't have to do a study then, would we? We could just measure everybody. Why randomly select when I've got a group of 14 and a group of 9? Done. However, that is an exceedingly rare occurrence when we actually have whole populations in front of us. It's exceedingly rare. It's like asking the question, am I significantly taller than Spencer? No, I'm just taller than him. It just is. Does he have significantly darker hair than me? No, he just has darker. What kind of stupid question is that? Not everything's a statistical question. Some things are just questions. Did I cut my thumb? Yes. Did I significantly cut? Those are pretty bad cuts. But it's not a statistical question. It happened. Okay, so sometimes you got to keep that in mind. But it's rare in science when we actually have all the possible cases of interest. That's a population. Excellent definition of population. All the cases of interest. When we have all the cases of interest in front of us, and we have the time and resources to measure them all, the neat thing is we don't need to do that. We can take samples and make a pretty good guess. So, there is reality that HO is true or HA is true. Then we make decisions. We either don't reject HO or we reject HO. We don't ever accept the alternative hypothesis because we don't have proof that the alternative is true. It's kind of like you're innocent until proved guilty, but you're never found innocent. You're found not guilty. Right? And that's a subtle but real difference. Right? Nobody's ever found not guilty. They're found innocent. They're found not guilty. O.J. Simpson is not guilty of killing his wife, but he killed her. Right? So, here's the kind of thing. First of all, we don't reject HO and HO's true. Correct decision. Sad decision. Unpleasant decision. Doesn't get published decision. Eventually leading to end of career. But no publications, no tenure, you get fired. So that's no good. But it happens. At least you didn't make a fool of yourself and do this. There are no psychics. Yes, there are! You just made an idiot of yourself. I'm not pregnant. Yes, I am! Wow. That's got pretty severe consequences, doesn't it? What do we do? And I'm not going to ask anybody here if you're taking it, but I'm sure some people in here have been involved in pregnancy tests. Either one way or the other, happy or sad. The first time you take a pregnancy test and it comes up positive, you go, well, I better get another one. Because I better be sure. Right? And you're either very excited, or you're always nervous. Making your own people is kind of a nervous. It's nervous. it's nervous work. Well, the actual making of the people. It's more when you find out. That was a little personal. But it is great when you have kids, though, because when you first, and you want to have kids, because it's like I don't need to make friends anymore. I can build my own people. Right? It's the greatest thing ever. But anyway, see, this is what I did. In my long-term plan to get more citations, a kid, and then she went in the same field as me, as we went to graduate school, she would cite my work, and it's going to help me, really. So it's all just selfishness. But do not reject HO, okay? But what if HA is true? That's a mistake. Call that a type 2 error. It's a mistake, but it's not as bad a mistake in a lot of respects, because someone else will make the correct decision. It's bad. It's career bad. It's like, I could have found this, and that guy found it. Bam. If I'm actually pregnant, that's really something. But female human, if I'm actually pregnant, yet my pregnancy test doesn't work, I get a false negative, I'm going to find out soon enough that I'm pregnant.
Why are you going on that show?
Going to that show, I just don't know I was pregnant. How did that happen to anybody? You're sitting around and going, well, boy, I've really put on weight in a very specific place. And nowhere else, it seems. Plus, it seems that the weight now moves around a lot. I didn't know I was pregnant. It amazes me. I guess, maybe, I don't know. It's weird. So, we can make a correct decision, and that's what we want to do here, even though it's not a happy one. It's not something that a null result isn't exciting. But at least you didn't make an idiot of yourself and say that there are psychics. Type 1 error. We reject HO when HO is actually true. Make a type 2 error. HA is true. We fail to reject HO. Right? That's a problem. It's probably not as big of an issue. Someone else will probably do the experiment and find it. Or maybe you'll try again. Okay? Now, this is the one we want to get. HA is true, and we reject HO. We want it to be the case that they come from two different groups. You don't do studies hoping for null results. Right? So you want that to happen. Questions so far? Again, I know you've gone over this stuff before, but so again, correct decision, HO true, fail to reject. HA true, do not reject. Type 2 error, HO true, reject HO. Type 1 error, HA true, reject HA. Best possible decision is a correct decision. Okay. So, how likely is it we're going to make one of these mistakes? It's okay. So we have some control of the situation. We set the probability of a type 1 error. We actually do that. We can do that. We set it at 0.05. So the likelihood of this happening is 5%. It's 5% chance. It's called alpha. And I apologize in advance for the fact that alpha and beta are going to mean something entirely different in about 3 weeks. Right now, alpha means this, okay? It's the probability of a type 1 error. The probability of a type 2 error is something we can't set. When we talk about power, I'll explain this, but we set, our methods are all, set up this way. The math is all set up this way. So, probability of a type 2 error depends on n, which is the number of subjects in the study. It depends on sigma, that's the population standard deviation, or sigma squared population variance. And it depends on alpha. Besides the probability of type 1 error. Okay? And that's called beta. Probability of type 2 error is beta. What you want ideally is small alpha, small beta. You don't want errors. So 1 minus beta is the probability of a correct rejection. That's power. Statistical power. That's statistical power. Questions so far? All right. We actually set, what would we set alpha at? Well, magically, we set it at 0.05. This is actually just because of a single person. R.A. Fisher, who was a biologist who did work on the first kin selection model, for those of you guys that took evolutionary psych with me or have taken some evolutionary biology, first kin selection model is R.A. Fisher. He also invented analysis of variance because he had no way to analyze his data, so he invented a new way to do it. So he's smart. And then a guy named John Tukey, we talked about Tukey, right? Remember Tukey was working on this guy invented exploratory data analysis. So, well, he coined the term, he invented it. Tukey apparently sends a telegram, because it's a long time ago. Not an email, not a text. Use Snapchat. Telegram to Fisher saying what percentage points of the F distribution are your students working on? In other words, what, the F table. Right? He said 0.05 was okay, we'll work on that too. That's where it comes from. Because they used to, when people did those, figured out the probabilities in those tables for F and T and all that, somebody did that for you. Like, somebody did calculus to figure stuff out. It's hard. So they had graduate students working on this night and day. These really hard integrals to do this, which is kind of neat. So it's totally because of that, though. So the reason today that we say this poll is accurate plus or minus 2.5 percentage points 19 times out of 20 is just because of R.A. Fisher. Because one guy did it that way. Had he said 0.03, we'd all be worrying about trying to get the 0.03 significance level. This shows how completely arbitrary and ridiculous this is. Right? And it is. It's arbitrary and ridiculous. I would say we might want to be more flexible. So let's say you have a situation where, let's say you're testing a new drug. It doesn't have a whole lot of side effects, and it's not for a horribly serious condition. Okay? Maybe you want to put the alpha at 0.06, 0.10, 0.1. So not a very serious, so let's say it's something like curing male pattern baldness. And it's got no side effects, we know that. What's the worst thing that can happen? Oh, some guy doesn't get hair grown back. Some guy who's like all obsessed with that, who cares? First of all, just grow up and realize who you are and just deal with it. That's the first thing. But if you're going to put cream on your head because of that, go ahead, go nuts. But really, it's not hurting anyone. On the other hand, let's say it's an AIDS drug. That's serious. And let's say it's got pretty nasty side effects. Well, We already have AIDS treatments that work pretty well. They don't cure AIDS yet. That'll come. But they work pretty well. We would want to have alpha a lot lower. Or let's say, on the other hand, let's say it's something like testing the water. When I lived in Corner Brook, we used to have boil orders every spring. For like a month, you could boil your water. For 5 minutes before you can drink it, or until you install the high-end filtration system in your home, which is what we do. That's most people end up doing eventually, because the further east you go in this country, the worse the water gets, and so does the color. The color gets brownish. It's true. It's funny. I remember coming to visit my parents in London, and we were living in Corner Brook, and I ran a bath for Maddie, who was mistakenly come here. She was like 5. And she said, "There's something wrong with the water." "It's clear, honey. Water here's clear." I mean, so it was something we had to do. And the fear was Giardia. You know what Giardia is? It's really unpleasant. In Newfoundland they call it beaver fever. It's from beaver droppings getting in the water supply. And it's exceedingly unpleasant. It can kill you if you're young or you're very old. And it's kind of like you poop and puke yourself to death. It's really unpleasant. And for people like all of us, it would just be an unpleasant 3 or 4 days of constantly being on the toilet and just deciding what end it's going to end up at this point. So it's not fun. So what you do is you boil your water. And you know what? I don't care if they set the alpha at 0.2 for that. The inconvenience of me boiling my water, and it's a false positive, beats the hell out of me. Right? So in that case, a public health issue. Secondhand smoke is like that. Secondhand smoke, not a single study has found a 0.05 effect saying that secondhand smoke is damaging to anybody. But you know what? It all goes in the same direction, and it's all at 0.07. It's like, yeah, it's probably not good for you. It seems exceedingly unlikely that it's even neutral. Right? I think it's getting a little silly saying people can't smoke inside. Don't smoke. By the way. And I'm one of those ex-smokers that isn't like, "You're worse than Hitler if you smoke." It's like, just if you want to smoke, go ahead, go nuts. I don't care. Just don't. You don't have to always. You're inside. Who cares? We live in a town making steel. You think that's not a problem? No, let's stop people from sucking on a butt if they want. Anyway, what I'm saying is, in that case, again, it's a public health issue. I'm probably going to be a little lenient with you. What's the worst thing if false positive happens? There aren't as many cigarette butts around. That's probably okay. Right? So we should probably be more flexible, but in typically we aren't. Typically we really aren't. What I would say here is, look, if you've got an effect, if you found something, let's say you found psychics, you better be putting that alpha lower than 0.05. And there's a whole other approach to statistics. It's called Bayesian statistics. That says that that's what we ought to be doing. Saying, look, if we've got extraordinary claims, we better have extraordinary evidence. And it doesn't work really the same as this a whole lot, but it's that kind of idea. It's not really. It's not just changing your alpha, Bayesian statistics. It's an entirely different approach. But let's say you've got an effect that goes with everything else you found in your research, and it's 0.06. What should stop you from interpreting that? I think, in fact, if it goes together with everything else you hypothesize and all your other effects, you should probably be able to say, yeah, that's right. I once got this on a review of an article. Do not discuss non-significant effects. It went along with everything else that I predicted. It went along literally with something some people have called the Broadbeck effect. Well, one guy called it. It wasn't me. We never caught on, which is sad. I discussed it. I said it was 0.0504. But what the hell? I thought to myself, look, it goes along with everything else that I've demonstrated 5 or 6 times. Other labs have demonstrated. It's a thing. It's out there. People are testing it. It works. If I had ran my birds for another freaking day, I would have been fine. I'm going to talk about it. Do not discuss non-significant effects. I wrote back and I said, fine, I'll take it out. You realize if I rounded that, it's 0.05, right? That was the same person that told me to change the name of, when I wrote subjects, to animals. Or no, sorry, to participants. APA says you can't call them subjects anymore. I said, they didn't sign up. I went out and caught them. They live in cages. They aren't people. So I think I was a little silly. And I think in hindsight, I probably should have. I was being a bit of an idiot when I put that in there. I probably just should have rounded it to 0.05. Because I was trying to be, honest. Have some integrity and what have you. But I thought, this will be fine. But you know what? That was just that one editor. He was also a very good person, by the way. A totally nice guy. I can't believe he was being such a... Because I know the guy. He's really a good guy. I haven't talked about him since. It kind of clearly it bothers me because 20-odd years later, it's still on a slide. So, I mean, we should be a little more flexible, and we really are with public health, things like that, they really are a lot more flexible. I know with the boil orders in Corner Brook, it was 0.15, because I asked somebody. They said one standard deviation, which is actually 0.16. Is that right? Yeah, 0.16, which I was like, I'm fine with that, that's great. 16% of the time, they're making me boil my water without need to. Oh, well, that's too bad. The whole time we lived there, we never got sick, though, which is good. And you think about that, with something like that, public health, there are cases, think of the Walkerton case down in Southern Ontario, people died. And that was for E. coli poisoning in the water. You can kill people with contaminated water. People die. And it's hard to die from majority of it. People do. People literally diarrhea themselves to death. Man, that's a great way to go. If that was going to happen, I'd be like, does anybody have a sword I can kill myself with? Because that sounds unpleasant. Questions about this stuff? Okay, that was a lot for the first full day. So we'll stop now. Unless you guys want to know more statistics, you're good? Yeah.
Dave.
Yeah.